In this example, we'll look at how FloEFD, a CAD-embedded CFD tool for Solid Edge, can be used to analyze the flow and thermal management problem of a new audio amplifier to ensure that it meets consumer electronics standards regarding its temperature distribution. Let's take a look at our Solid Edge model. You will notice that because of the FloEFD add-in, there are a few additions to the interface, like the Flow Analysis tab for the command ribbon and the FloEFD tab for the edge bar. What you will see as we set up the CFD problem and ultimately look at the results is that FloEFD ends up feeling like an extension of your already familiar Solid Edge environment. And one of the keys to that is being able to work directly with your native Solid Edge model. A convenient way to create a FloEFD project is to use the wizard, which guides you through the setup of the basic definition of your analysis. First, you will name the project. Then, select the unit system. Next, you will define the analysis type. In this case, the amp is cooled by a fan, so the forced convection cooling within the box will be the focus of the analysis, and we'll define this case as an internal flow problem. Also, we want to include conduction effects, so we will select heat transfer in solids. Next, we'll choose the fluid in the analysis to be air, and select aluminum as the default material. And even though we are not modeling the airspace around the amp, in this example, we can still include the effects of natural convection by applying a heat transfer coefficient in ambient temperature. We'll set some initial conditions and finish the wizard, which will create our project in the FloEFD tree named Case 1. Now we need to finish setting up the model by assigning the remaining inputs. We can see that the computational domain is recognizing the model properly, so we can go ahead and hide it, and get started by assigning materials to the components that are not made of the default material of aluminum. So we'll select the PCB and assign it an anisotropic material property, since the conduction in the PCBs is typically different in the through plane and in plane directions. We'll also pick the transistors for this amp and assign a different material to them. Since this amp is modeled as an internal flow case cooled by a fan, we need to assign a boundary condition to the slots where the air can exit the enclosure. We have put lids over the openings of the enclosure at the inlet and outlets, and these serve the purposes of isolating the empty space within the amp that FloEFD can identify as the airspace, and also give us faces to apply boundary conditions to. Another boundary condition we'll assign is to apply a temperature condition to the outside case along the two mounting faces of the amp. So for this, we'll again insert a boundary condition, and we'll change the type to be a wall condition, and then assign the appropriate temperature of 25 degrees C. Next, we want to add a fan to force air through our amp enclosure. We'll move over to the lid at the inlet to the amp and select the annular shaped face on the inside of the lid and assign a fan curve to it. And we'll include a rotational component to the incoming flow by adding swirl. Now we need to assign the heat sources. We'll select the 4 transistors and assign an overall heat generation rate to them of 20 watts. Next, we'll select the capacitors and give them a total heat generation rate of 10 watts. The remaining heat produced by the electronics we'll assume can be distributed across the PCB. Next, we will assign some goals, which serve a couple of purposes. One, they are a way of extracting from the analysis quantities of interest. For example, we want to know how hot the transistors will get. So we will assign a volume goal of average and max solid temperature for these components. Similarly, we want to know, based on the fan curve that we assigned, what the eventual flow rate is that is produced by this fan. So we can assign a volume flow rate goal to the fan face. The other purpose of goals is to help guide the convergence of the run, meaning that the solver will look for these goals to reach a steady state solution before determining that the solver phase of the analysis is complete. Lastly, we'll take a look at our mesh settings. One of the core strengths of FloEFD, which overcomes a long-standing bottleneck in the CFD process, is its meshing approach. Let's look at the global mesh settings. The most common option is to use the automatic approach, which uses a slider bar to control the mesh fidelity. Through this simple approach, FloEFD can mesh a wide range of complex geometry easily. And more advanced meshing options like local meshing and solution adaptive refinement are available as well. Now that we have set up our problem, we are ready to run the analysis. This is the number crunching phase of the process, where the software will determine what solid and fluid volumes need to be considered, create a mesh that captures these geometries, and then solve the appropriate equations to reach a solution for the flow and thermal fields. This process can be tracked from the Solver Monitor window, which lets you chart the progress of your run, preview the solution at each iteration on various planes, and graph the convergence of your goals. When the analysis is complete, the run will stop, and you can start to look at the solution on your Solid Edge model. Let's take a look at the flow field through the enclosure, and a nice way of showing this is through cut plots. We'll start by looking at the velocity field, with vectors showing the direction of the flow and the colors showing the speed of the air. As you can see, the fan is positioned to direct flow onto the heatsink, which it does effectively. However, a lot of the flow bypasses the rest of the electronic components on the board. If we switch our plot to display temperature, we can see the effect of this. The portion of the board in the middle with low speed flow is relatively hot. Another way of looking at the temperature distribution more three-dimensionally is to create a surface plot. In our first plot, we will look at the temperature on the outside of the enclosure, which needs to be kept below a certain value to stay within consumer electronic standards. We can rotate the model to see the temperature distribution, as well as use our probe tool to conveniently extract the temperature at locations of interest. Let's also look at the temperatures on the components inside the enclosure. Again, we can see the higher temperatures around the center of the board. Another powerful viewing option is to look at flow trajectories. These can be animated to give an overall picture of how the air flows through this device. And notice that with all of these viewing options, you can see the CFD solution directly in the context of your Solid Edge model. So in looking at the results from our first case, we want to make some design changes to improve the cooling effectiveness. And this is where the advantages of working directly with the Solid Edge model drastically reduce the amount of time and effort required to explore the design space with CFD. One of the ideas that we would like to test based on our first solution is to shift the fan slightly towards the center of the amp. We are hoping to divert a portion of the incoming airflow more towards the central region of the board while still maintaining strong flow through the heatsink. Additionally, we'll go ahead and increase the length of the heatsink fins to further help cool the transistors. So we have set up a second family of assemblies member in Solid Edge that reflect these design changes. Now, all we need to do is clone the setup from our first case to the new design, which we'll call Case 2. This new case now has the same setup as Case 1, so we are ready to run our next test. After running Case 2, we can look at the solution to see the effects of the new design. Our cut plot shows that there appears to be more flow diverted to the center of the board, and that region appears to be cooler. We can see the same effect when viewing the surface plot. And a convenient way to more directly compare the results for the two cases is to use the Compare tool. From here, we can choose the items that we would like to compare, which for this example would be the active scene, which is the plot that is currently displayed on the screen, as well as the goals information. Using this tool, we can go to the Active Scene tab and see the same plot for both Case 1 and Case 2 next to each other. In our instance, Case 2 is displayed first, since that is the project from which we ran the Compare tool. You can see clearly that the temperatures on the board have decreased in Case 2. If we want to quantify the temperature reduction of our key components, the transistors, we can go to the tab that shows the comparison of the goals. Again, you can see that the temperature for Case 2 is substantially improved. This example shows how FloEFD for Solid Edge can be used to improve the design of an audio amp relative to thermal management. FloEFD puts the power of CFD directly in the hands of Solid Edge users with an easy-to-use, fast, and accurate analysis tool.